So now you guys must have definitely understood what is meant by the physical interpretation of friction factor, heat transfer coefficient and mass transfer coefficient in depth. So now let's proceed further. Now we will derive Reynolds analogy with the help of these three physical interpretations. So let's start with the friction factor. The friction factor relation is given as half into friction factor into Reynolds number is equals to characteristic length divided by thickness. This we can rearrange and write it as characteristic length is equals to half F Re into delta. So this will be our equation 1. Similarly, from the physical interpretation of heat transfer coefficient, we know that heat transfer coefficient H is equals to K by delta T, where K is the thermal conductivity and delta T is nothing but the thickness. And we are also familiar with the dimensionless number, that is Nusselt number. Nusselt number is equals to H LCH by K, where LCH is characteristic length, K is thermal conductivity and H is nothing but heat transfer coefficient. This we will write in terms of characteristic length. All equations we will write in terms of characteristic length. So equation 2 becomes characteristic length will be equal to Nusselt number into delta T, which is nothing but the thickness. Similarly, from the physical interpretation of mass transfer coefficient, we got Kc is equal to dAb by delta C. Here dAb is nothing but the diffusion coefficient and delta C is the thickness. And we also know Nusselt number for mass transfer coefficient, which is equal to Kc LCH by dAb, where LCH is characteristic length, dAb is diffusivity and Kc is the mass transfer coefficient. The Nusselt number for mass transfer coefficient is also known as Sherwood number. Again, we will arrange this equation in terms of characteristic length, which will give us equation 3, that is Sherwood number into delta C, which is thickness. So we will combine all these three equations which we just wrote. So from this we get all three equations in terms of LCH and we equate them. So we get 4a equation as LCH, that is characteristic length, will be equal to half into friction factor into Reynolds number into thickness, which will be equal to Nusselt number into thickness, which will be further equal to Sherwood number into thickness. Next, we will rearrange this equation, that is, we will divide the whole equation by Reynolds number. Here, if we divide by Reynolds number, it will get cancelled. So we are left with half into friction factor into delta. Similarly, here we will get Nu by Re delta T and here Sh by Re delta C. So this will be our equation 4b. Continuing further, we know 4b equation as we have already derived, that is half F delta is equals to Nu by Re delta T is equals to Sh by Re delta C. Now we already know that Stanton number for heat transfer can be written in the form of other dimensionless numbers, that is Nusselt number, Reynolds number and Prandtl number. So it can be written as Stanton number for heat transfer is equals to Nu by Re multiplied by Pr. Similarly, Stanton number for mass transfer can be written in terms of Sherwood number, Reynolds number and Smith number, which can be written as Sh by Resc. So substituting these two equations in 4b and combining all the equations, we get the final generalized form of transport analogy, that is half F delta is equals to Stanton number for heat transfer multiplied by Prandtl number multiplied by thickness, which is equals to Stanton number for mass transfer multiplied by Smith number multiplied by thickness. So this is a generalized form of transport analogy. Now, for the further derivation of Reynolds analogy, we need to assume two conditions. The first assumption is that all the thickness should be considered to be equal, that is delta T and delta C. All these should be considered to be equal. So if we substitute this assumption in equation 4c, all those terms get cancelled and finally we get this equation, that is F by 2 is equals to Stanton number for heat transfer into Prandtl number, which is equals to Stanton number for mass transfer into Smith number. So after looking at assumption 1, which was considering all three thicknesses to be equal, the assumption 2 is we consider the dimensionless numbers to be equal, not all, but Prandtl number and Smith number they both are considered to be equal and equal to 1. So again substituting this assumption 2 in the main form, generalized form of transport analogy, we get this equation. F by 2 is equals to Stanton number for heat transfer is equals to Stanton number for mass transfer. So the generalized form of transport analogy, the whole equation reduces in terms of three factors, that is friction factor, Stanton number for heat transfer and Stanton number for mass transfer. So this equation is known as Reynolds analogy. So with the help of transport analogies, we have derived Reynolds analogy with the help of two assumptions. And one thing to keep in mind is that this equation is valid only for gases. So I am damn sure that you must have definitely understood the derivation of Reynolds analogy. In the similar way, we will derive Chilton-Coulomb analogy. Now, you are very familiar with the generalized form of transport analogy because we have derived this in the previous section. The generalized form is given as half into friction factor into thickness is equals to STH, that is Stanton number for heat transfer, multiplied by Prandtl number multiplied by thickness, which is equals to Stanton number for mass transfer multiplied by Smith number multiplied by thickness. So in the previous derivation of Reynolds analogy, we assumed that all these three thicknesses were equal, but here the assumption is different. Here we assume the thickness delta by delta T as Prandtl number to the power 1 by 3. Similarly, the thickness ratio delta by delta C is equals to Smith number to the power 1 by 3. So, if we substitute all these values in the generalized form of transport analogy, we get these two forms of equation, that is F by 2 is equals to Stanton number for heat transfer multiplied by Prandtl number to the power 2 by 3, and this we denote as JH. Later you will know what is meant by JH. Similarly, we get another equation by substituting delta by delta C is equal to SC to the power 1 by 3 in the generalized form equation, and we get it as F by 2 is equals to Stanton number for mass transfer multiplied by Smith number to the power 2 by 3, which is denoted as Jm. Now here JH and Jm are the Coulomb J factors for heat and mass transfer. This you have already studied in the first part of our podcast. Next, the limitations of these two equations is that the range of Prandtl number should be between 0.6 to 60 and the range for Smith number should be between 0.6 to 3000. So these are the limitations for Chilton-Coulomb analogy, and these are the two equations. So after the derivation of Chilton-Coulomb analogy, let's look at its geometric limitations. So these are the four types of flow geometry which are given and the corresponding Chilton-Coulomb analogy. So let's look at them one by one. First one is a flow over flat plate. So for the flow over flat plate, the Chilton-Coulomb analogy is given as F by 2 is equals to JH is equals to Jm. You are already familiar with the terms J, which are J factors. Next, the flow geometry is flow over a cylinder. For them, the Coulomb factors JH and Jm are equal. Here, the term F by 2 is neglected. Third, flow over a sphere. We have the same relationship, that is JH is equals to Jm. But here we have two conditions. This will be true if and only if Nusselt number and Sherwood number are greater than equal to 2. The last one, the flow geometry, is flow in a pipe. For flow in a pipe, we have relation same as a flow over flat plate, that is F by 2 is equals to JH is equals to Jm. But we have a condition. The Reynolds number should be greater than 10,000, that is smooth pipe. So this is the condition, and this is the overall geometric limitation for Chilton-Coulomb analogy. Now let's move to the most important part of our podcast, that is solving problems. Any concept cannot be 100% understood if we don't solve any problems related to it. So to complete that, let's start solving problems. You can see on my right side there is a problem. So let's first read out the problem. The problem states that air at 20 degrees Celsius flows through a smooth pipe whose diameter is given to be 0.1 meter at 10 meter per second. The pipe wall is maintained at 80 degrees centigrade and is coated with naphthalene which sublimates into the air. So given air properties are given at 50 degrees centigrade field temperature. Viscosity is given to be 1.8 into 10 to the power minus 5 meter square per second. Prandtl number is given to be 0.71. The naphthalene properties are given below. Smith number is given as 2.6 and diffusivity is given to be 6.1 into 10 to the power minus 6 meter square per second. So now this is the given data. So what do we need to calculate? In the first part, we need to calculate Reynolds number and flow regime. Flow regime is nothing but just we need to state whether it's turbulent flow, laminar flow or transient flow. So the B part is we need to use Chilton-Coolban analogy and find Nusselt number and heat transfer coefficient. And the last part of the question is we need to use the same analogy and compute Sherwood number and mass transfer coefficient. So this is the overall question, given data and the things which we need to calculate. So I am damn sure that you must have definitely understood what the problem is, what are various doubts related to it, the given data and the questions asked. So the first part of the question is to calculate Reynolds number. Now by this time you must be very familiar with what is Reynolds number and its formula. Reynolds number is given by Vd by nu. V stands for velocity, d is the diameter and nu is the kinematic viscosity. Velocity is given in the question which is 10 meter per second and diameter is given to be 0.1 meter. The kinematic viscosity is given as 1.8 into 10 to the power minus 5 meter square per second. As Reynolds number is dimensionless quantity, we get Reynolds number as 5.56 into 10 to the power 4. Now this Reynolds number is less than 5 into 10 to the power 5. So we can conclude that it is a laminar flow. So the first part of our question gets completed. The next part of the question is to find heat transfer coefficient. For that we need Nusselt number, for that we need Prandtl number and then for that we need friction factor. So first of all we will calculate friction factor for laminar flow with the help of Reynolds number. The formula for laminar flow friction factor is given as F is equals to 1.328 into Reynolds number to the power minus 1 by 2, which is given as 1.328 into 5.56 into 10 to the power 4 whole power minus 1 by 2. After calculating this value, we get friction factor as 5.63 into 10 to the power minus 3. Now, using Chilton-Coolban analogy, we know this relation of friction factor, Stanton number and Prandtl number, which is given as F by 2 is equals to Stanton number into Prandtl number to the power 2 by 3. Substituting all the values, we get Stanton number as 5.63 divided by 2 multiplied by 1 divided by 0.71 to the power 2 by 3. After calculating this, we get Stanton number as 3.53 into 10 to the power minus 3. Next, we need to find Nusselt number. We know Nusselt number is equals to Stanton number into Reynolds number into Prandtl number. So we have just calculated Stanton number. Reynolds number is already calculated in part A and Prandtl number is given in the question. So substituting all these values, we get Nusselt number as 139.35. Now the question becomes more easy. We need to find heat transfer coefficient. For that, formula is already given, Nu K by D, where K is thermal conductivity. Here we just need to substitute all the values we have just found. Nusselt number we have calculated to be 139.35. Thermal conductivity is given in the question and D is the diameter. Substituting these values, we get heat transfer coefficient as 39.01 watt per meter square Kelvin. So we have solved part A and part B of the question. Now let's proceed to part C. In the part C, we need to find mass transfer coefficient. So let's go step by step. First of all, we need to use Chilton-Coolban analogy for mass transfer. From this, we will get Stanton number for mass transfer. So the formula of Chilton-Coolban analogy, as you all are familiar with, is F by 2 is equals to Stanton number for mass transfer multiplied by Smith number to the power 2 by 3. So substituting the values of Smith number and friction factor, we get Stanton number for mass transfer as 1.48 into 10 to the power minus 3. Next, we need Sherwood number. So the formula for Sherwood number is given as Stanton number for mass transfer multiplied by Reynolds number multiplied by Smith number. So substituting all these values, we get Sherwood number as 213.94. Now this is the final step where we will calculate mass transfer coefficient. To calculate mass transfer coefficient, we need Sherwood number, diffusion coefficient and diameter. Sherwood number we have just calculated, which is 213.94. Diffusion coefficient is given in the question, that is 6.1 into 10 to the power minus 6, and diameter is 0.1 meter. So substituting all the values, we get final mass transfer coefficient as 0.03, and the unit of mass transfer coefficient is meter per second. So this is the overall solution of the question.
Now, as we have seen the question 1, calculated the Reynolds number and the other terms related to it. Now, we are going to see the problem 2. This problem is about flat plate with variable wall temperature. The scenario discussed in this question is given as a 3 meter long flat plate is exposed to engine oil at 30 degrees Celsius, flowing at 2 meter per second. The plate's temperature varies as T, which is a function of x, is equal to 50 plus 20x, the whole is in degrees Celsius, where x is the distance from the leading edge. The given parameters discussed in this question are: first one, the oil properties at 40 degrees Celsius. The kinematic viscosity for this is given as 2.4 into 10 to the power minus 4 meter square per second, and the Prandtl number is given as 300. Now, there are 4 parts asked in this question. In first part, it is said that determine the Reynolds number at x is equal to 3 meter and the flow regime. It's similar as we calculated in the part A as calculated in the question 1. Now, the part B of this question. Using Chilton-Colburn analogy, derive the local Nusselt number at x is equal to 1.5 meter. Note, we have to calculate the local Nusselt number and not the average Nusselt number. Part 3. Find the local heat flux at x is equal to 1.5 meter. Part D is given as explain how the analogy handles variable wall temperature conditions.
As we have understood the question and doubts related to it, let's dive into the solution. So, the part A of the solution states that we need to find Reynolds number at x equal to 3 meter and its flow regime. So, as we all are familiar with the formula of Reynolds number, which is given as velocity into length by kinematic viscosity. All these terms are already given in the question. Velocity is given as 2 meter per second. Length is given as 3 meter and kinematic viscosity is given as 2.4 into 10 to the power minus 4, which has units of meter square per second. After calculating all this, we get Reynolds number as 25,000. So as the value is less than 5 into 10 to the power 5, we get its flow regime as laminar flow. So this is done for part A. Next, we look at the part B. In part B, we need to find local Nusselt number but using Chilton-Colburn analogy. But for that, first of all, we need to find Reynolds number at x equal to 1.5 meter. In question x at 1.5 meter, we find Reynolds number, which is given as the same formula as we used in part A. So using x is equal to 1.5 meter, we get Reynolds number as 2 into 1.5 divided by 2.4 into 10 to the power minus 4. The value of Reynolds number at x equal to 1.5 meter comes to be 12,500, which also indicates it is a laminar flow. So at this Reynolds number value, we use Chilton-Colburn analogy and we get a Nusselt number formula as 0.332 into Rex to the power 1 by 2 into Prandtl number to the power 1 by 3. Now this is a formula for local Nusselt number, which the same is asked in the question. So we substitute all the values, that is Reynolds number as 12,500 and Prandtl number as 300. And after substituting all the values, we get local Nusselt number as 91.3. Now after looking at part A and part B, let's solve part C. In part C, we need to find local heat flux at x is equal to 1.5 meter. So for finding heat flux, we need to first find heat transfer coefficient, which is denoted by h of x, which is given by Nusselt number into thermal conductivity divided by the distance, and the distance is given to be 1.5 meter. Nusselt number is given in the question as 91.3 and thermal conductivity is given as 0.145. Substituting all these values in the formula, we get heat transfer coefficient as 8.83 watt per meter square Kelvin. Now, to find local heat flux, we have the formula of heat transfer coefficient into Tw minus T infinity. Tw is given in the question as 50 plus 20x, which means it varies with the distance x. But here we need to find for value x equal to 1.5. So we substitute that value in the given statement, which is 50 plus 20x becomes 50 plus 20 into 1.5. T infinity is given in the question as 30 degrees centigrade. So we substitute all these values and we get local heat flux at x equal to 1.5 meter as 441.5 watt per meter square.